All right, today's learning objective is to look at what is called an antiderivative. An antiderivative is the same thing as an indefinite integral. We've talked about integrals as being an area. An indefinite integral just kind of gives you a function versus an actual numeric value. And so these are, sorry, I was waiting for my pen to load up there. An antiderivative is a function. An indefinite integral is also a function because they are basically the same thing. So let's talk about this word antiderivative. It means the opposite of a derivative. So if I have a derivative, I'm going to call my derivative dy dx equals 3x plus 4. What I have here, dy over dx, remember that was one of our ways to make a derivative or a symbol for derivative. What happens with antiderivatives is I have to solve this. I'm going to say dy equals 3x plus 4 times dx. Now hopefully you kind of remember how we had dx on all of our definite integrals when we did Riemann sums. Now this is what we call a differential equation. I've said that word a lot of times before, but this is your differential, equation. Remember how we talked about in college, there's a whole course called DiffEq. It is surrounded by these differential equations. Basically, you have a derivative of y and you have the variable x with respect to x over here. So to solve a differential equation, we're going to use, so to solve this, we have to find what's called the antiderivative. Okay, and we will talk about techniques for that later on. But really, what we do is we say, well, what if this differential equation dy equals 3x plus 4 dx is actually a function? Let's just call it f of x equals 3x plus 4 dx. The antiderivative of this, and this is some symbols that they use, if this is my original function, the antiderivative we use a capital F for. So my derivative, as I like to say, what I would normally call my derivative, like this, they just use the function notation. So the capital F is your antiderivative. The antiderivative of that is 3x squared over 2 plus 4x. Okay? And I'll teach you how to do that in a little bit. But what you need to know is this works because if I take the derivative with respect to x of 3x squared over 2 plus 4x, if I take that derivative, I multiply by 2, things cancel, I get 3x here, and the derivative of 4x is 4, I get plus 4. So that's how I know that this capital F of x function, this is the antiderivative of 3x plus 4 dx. Okay, so like I said, they use a little f for their differential equations in this section for a while, and then a capital F for antiderivative. A lot of times what I've been using is I use this notation for derivative, and then my antiderivative would be my original function, which is f of x, which they're all going to be the same thing here in a little bit, so don't let the capital freak you out too much. By the way, this right here, this answer, is only one of many answers that could be the antiderivative. If this is my differential equation, 3x plus 4 dx, and I find this to be my antiderivative, that's what we call just one of many solutions. See, I could have 3x squared over 2 plus 4x plus 6. That could be one of my solutions. I could have 3x squared over 2 plus 4x plus or minus 15. Because this is a constant, and remember, when you take the derivative of a constant, you get 0. This is what we call a general solution. This is a general solution right here. And these are more specific when you actually have a constant with them. And that's what we're going to look at. A lot of times when I find an antiderivative, so if I have a function, we'll say, I'm just going to use 3x again, dx. Its antiderivative is 3x squared over 2. What we do, and you'll see this in funny math jokes all the time and little things, is we add a plus c. So this right here is what I call a general solution. This plus c means some constant. We call it this, basically we call it the general constant, because it can be any number. It just could not be a function. It could not be a variable. And it's a lot of times called the constant of integration. And I'm going to show you why it's called that in just a second, because finding the antiderivative is the same as integrating. So remember our symbol for integration? If I integrate 3x dx, that gives me 3x squared over 2 plus some constant of integration. This again is my general solution. So integrating indefinitely, meaning I don't have an upper or lower boundaries, is the same as finding my antiderivative. Okay, one thing that we talk about if you take a Diff-EQ class, and even in Calc 2 and a little bit for this class, we talk about, instead of having this general answer, this general solution, maybe I want something called a particular solution. And all that means, a particular solution means that I'm going to find C. A particular solution means you have to find C. In order to find C, they would have to give you more information. Okay, so let's say I have this, dy equals 3x dx. That's the one I've been using. And I want to find the particular solution at the point, let's just use 1, 3 for an ordered pair. So what I do is I integrate. Now here's the cool thing. This is how we get this. When I integrate this, and we look at this more in Calc 2, but when I integrate just dy, I get y. So I get y equals, if I integrate 3x, we've already done this, we get 3x squared over 2 plus c. Well, they want the particular solution, so that means I need to plug this guy in. So y equals 3, so 3 equals 3 times 1 squared over 2 plus c. So if I solve that, c is 1.5 or 3 halves. So my particular solution would be y equals 3x squared over 2 plus 1.5 or plus 3 halves. That's my particular solution. So that's the difference between a particular solution and a general solution. Now, this is the point where I need you to make sure that you write down your rules. There's some rules in your book, page 250. They're called rules for integration or antiderivatives. These are rules, just like derivative rules, that you're going to be required to know. And before we go any further, what you need to understand, and I think I've said this, but integration and derivatives are kind of like inverse properties. So if I take the derivative of an integral, so I'm integrating this function, but then I take the derivative after I integrate, I get back the original function. Okay? The same thing could be said a different way. If I integrate a derivative, and I'm going to use a capital F to show that it's the derivative of the antiderivative. If I integrate this, and it starts as a derivative, when I get it back, it's just going to be my original function plus c. Okay? So they're basically inverse operations, derivatives and integrals. All right, so make sure you write those rules down. I'm just going to show you some examples. So I would pause, write those rules down from 250. If you don't have your book, maybe Google rules for integration. The first one I'm going to look at is constant. So I'm going to integrate just 4 dx. Now, how it's different is this, if I integrate 4 dx, that's the same as saying 4 times the integral of dx. Remember how we talked about you can move that out there? Well, if I integrate just dx, I get back x. So I get 4, and this value is just x plus some c value that I don't know. Okay, so there's one example. Another example to integrate, 5x squared dx. First thing we'd want to do is move that 5 in front. 5 times the integral of x squared dx. Well, this is called the power rule for integration. The 5 stays in front. And what you do is you have to add 1 to your power. With derivatives, we subtract 1. With integrals, we add 1. So we add 1. So it becomes x to the third. And then I have to divide by my power. Because we always multiply and subtract with derivatives. So with integrals, I add and divide. So it'd be 3 here, and then I'd have to divide by 3. So it'd be 5x cubed over 3 plus c. Okay? What if I have the 5x minus 4x squared dx. This is a big one we use a lot. What you do is you break this into two. I'd make it 5 times the integral of x minus 4 times the integral of x squared. Oh, I forgot my dx's. I do that a lot. You can yell at me for it. Not really, but you can pretend to yell at me for it. All right, so if I integrate this, I have a power of 1. So if I add 1, 1 plus 1 is 2. So I get x, come on, pen, x squared, and I have to divide by the power is 2, minus 4. Here if I add 1, that's 3. So x cubed over 3 plus c, because this is a general solution because it's indefinite. So I would just rewrite it as 5x squared all over 2 minus 4x cubed all over 3 plus c. Okay, let me show you one more. If I integrate 1 over x cubed dx, this one calls for a rewriting. So the same as integrating x to the negative third dx. Same power rule though. What you do is you add 1. So negative 3 plus 1 is negative 2. So I get x to the negative 2, and then I have to divide by the power. The power is negative 2. So if I simplify that and make it look nicer, I get 1 over negative 2x squared plus some constant of integration. All right. That'll be it. Make sure you check out the sine, cosine, tangent ones too. They all have rules just like derivatives. See you in class. Have a good day.